Picture a sealed box, inside a cat, a vial of poison, a quantum trigger, the famous thought experiment that made physicists squirm and philosophers grin. For a moment before anyone opens the lid, the cat is both alive and dead in the language of quantum theory. A superposition of two very different fates. The act of opening the lid, or measurement, forces the two possibilities to collapse into one. The cat is either alive or dead. That's one widely accepted interpretation, but there are alternatives. Now imagine that those two fates are collapsed into one long before the lid is opened, not due to measurement, but by space-time itself. One branch of the superposition pulls space-time one way, the other branch pulls it another way. Someone asked, could gravity, the thing that curves space and time, be the force that makes the two geometries incompatible and unstable, and force the universe to choose? In that picture, the cat's life or death is not decided by an observer's glance, but by a whisper of gravity that makes the two possible worlds collapse into one. That is the kind of question at the heart of quantum mechanics. And it is the kind of question that makes physicists, philosophers, and late-night thinkers sit up and listen. Quantum theory gives us a recipe for probabilities. It hands us a mathematical object called a wave function, a cloud of possibilities, and tells us how those possibilities evolve. The wave function predicts the odds of different outcomes, and it does so with breathtaking accuracy. But it does tell us why, in any single experiment, one outcome happens and not another. When you measure, the wave function seems to collapse into a single result. Is that collapse a real physical event, or is it just a change in our knowledge? Physicists have argued about this for a century. Some answers are pragmatic. Treat the wave function as a tool for predicting observations, and stop asking metaphysical questions. Niels Bohr's Copenhagen view is in the spirit. Quantum rules apply, and the classical world emerges when measurements are made. Some answers are extravagant. Hugh Everett's Many Worlds theory says there is no collapse. Every possibility is realized in a branching multiverse, and we happen to find ourselves in one branch. And some answers are radical in a different way. Maybe collapse is a real physical process. And if so, what causes it? In the 80s, some scientists proposed a bold idea: add a tiny bit of randomness to quantum dynamics so that wave functions occasionally and spontaneously localize. Their models were designed so that microscopic particles remain quantum for a long time, but macroscopic objects like cats, coins, and planets are forced into definite states almost instantly. These models are not interpretations. They are modifications of quantum mechanics that make new testable predictions. Roger Penrose offered a different intuitive thought. Gravity might be the trigger. If a mass is in two places at once, each branch produces its own gravitational field. Perhaps those competing space-time curvatures cannot coexist forever. He proposed a simple estimate for the collapse time, roughly h bar divided by delta Eg, where h bar is the reduced Planck's constant, and delta Eg is the gravitational self-energy difference between the branches. Later, Dixie offered a detailed mathematical model along the same lines as gravity. The force that shapes galaxies might also be the hand that paints the single stroke of reality. To test such ideas, theorists had to make them concrete. That required a technical fix. The collapse noise cannot act at arbitrarily small scales without producing mathematical and physical problems. So models introduce a short distance smoothing length called R0, a cutoff that says the collapse acts over that scale. The value of that parameter matters enormously. If it's tiny, on the order of a nucleon radius, about 10 to the power of minus 15 meters, the collapse acts at very small natural scales. Such models can be thought of parameter-free and based on fundamental physical laws. Why does this technical parameter matter for experiments? Because many collapse models predict that particles will undergo a tiny continuous jitter as they interact with the collapse noise field, a Brownian-Sunton-like motion. If those particles are charged, their jitter produces electromagnetic radiation, a faint, steady stream of photons. In many versions of the models, that radiation would be in the X-ray range. Detect that radiation, and you have caught collapse in the act. Now, enter the underground detectors. They are the same instruments built to hunt neutrinos and dark matter, comprised of arrays of ultra-C-pure germanium detectors, shielded by kilometers of rock. These instruments are exquisitely sensitive to faint signals. Clever physicists realized these detectors could be used as collapse detectors. Teams at deep underground labs looked for the predicted X-ray glow, subtracted known backgrounds that may come from natural radioactivity, cosmic muons, the usual suspects. The question asked is this: is there an unexplained excessive radiation that matches the collapse prediction? The answer so far has been no. The experiments found no such glow at the sensitivity needed to exclude the simplest parameter-free versions of the gravity collapse idea. In plain terms, the cleanest, most natural instantiation of the Deal-Penrose picture, the one that did not hide behind adjustable cutoffs, is falsified by data. But science is rarely a single knockout punch. If you allow the smoothing parameter R0 to be larger, the predicted radiation becomes weaker, and the models survive the experimental bounds. That rescue comes at a cost. When R0 is treated as a free parameter, the model becomes phenomenological. It fits observations by tuning knobs, rather than deriving them from first principles. Some physicists find that unsatisfying. A theory that needs a hand-picked cutoff feels less like a deep law and more like an effective description. Useful, perhaps. But not the final word. There's another subtlety worth savoring. Those collapse models have two linked layers. The first is a stochastic state vector rule, where in a single run, random noise nudges the quantum state toward one definite branch. The second is the ensemble description, the density matrix master equation you get by averaging over the noise, which produces decoherence as a consequence of those random jiggles. The master equation is what experiments test. The stochastic story is what gives the model its metaphysical bite. If the ensemble shows no extra radiation, the stochastic story is constrained. So where does that leave us philosophically? If gravity is not the collapse trigger in its simplest form, we have several paths forward. Each with its own flavor. One path is modesty. Treat the wave function as a tool for predicting observations. The world looks classical because branches stop interfering. The quote-unquote collapse is an update of knowledge. This is tidy and empirically conservative, but it leaves a metaphysical itch. Why does a single outcome occur in a single run? Another path is extravagance. Embrace many worlds. There is no collapse. Every possibility is real in its own branch. It solves a measurement problem by dissolving it into a vast multiverse, but it asks us to accept a reality far larger and stranger than everyday intuition. A third path is mystery. Some have speculated that consciousness plays a role in collapse. This idea is controversial and lacks empirical support. But it persists because the measurement problem is stubborn, and because consciousness is the most intimate mystery we know. A fourth path is patience and humility. Maybe we need a deeper theory, a full theory of quantum gravity, or a new framework that will show how space-time and quantum states co-emerge and how definite outcomes arise. That would be the cleanest resolution, but it is also the hardest to reach. What should we take away from the recent experimental push? First, the scientific method is alive, and bold metaphysical ideas can be turned into concrete predictions and tested. The simplest gravity collapse story has been squeezed by data. Modified versions survive, but at the price of extra parameters and philosophical unease. Second, the measurement problem is not a mere technicality. It is a question that touches our everyday sense of reality, whether the world is a single, definite thing or a branching multiverse, or something else entirely matters for how we think about facts, agency, and the nature of existence. And finally, there is beauty in the open question. The fact that the curtain has not yet fallen means there is still room for wonder, for new experiments, for fresh ideas, maybe the next generation of tabletop experiments levitated nanoparticles, optomechanical resonators, clever interferometers will probe the remaining parameter space. Maybe a theoretical breakthrough will show how gravity and quantum mechanics reconcile in a way that naturally produces single outcomes. Or maybe the answer will be stranger than we imagine, such as the whole universe really comes into being due to our consciousness. If you close your eyes and picture that quantum cat, remember this. The cat is not just a quirky thought experiment. It is a mirror held up to our deepest assumptions about reality. The underground detectors are the stagehands listening in the dark to see whether gravity pulls the curtain closed. For now, the curtain still hangs, the show goes on. And the question, is that cat really both alive and dead before the lid is opened, remains one of the most intimate and profound mysteries we can ask.